Hello friends, welcome to H2 Event Academy. In the last lecture, we have discussed about the reduction of a system of forces to a single force and a couple. Also, we have discussed about the change of the base point. Okay, so let us move further. So we have what are the conditions? Okay, so what are the necessary and sufficient conditions of equilibrium of a rigid body under the action of a system of forces acting at any points of it? Okay, so let us discuss this. So we have the theorem as the necessary and sufficient condition of equilibrium of a rigid body under the action of a system of forces acting at any points of it are that the sum of resolved parts of the forces along any three mutually perpendicular axes and the sum of moment of the forces about these axes must vanish separately. Okay, so how we can prove this? So we have, okay, so let us consider a system of forces. Let us consider the system of forces as F1, F2, F3, Fn. Okay, and these are acting at point acting at points A1, A2, A3, En. Okay, and let the position vectors of these points are A1, A2, An. Okay, so this whole system of forces, this will be equivalent to resultant are single force. This is a single force equivalent to a single force R. This will be equivalent to a single force R plus a couple of moment G. Okay, so we have R is equal to summation R is equal to 1 to n Fr. Okay, and G is equal to summation R is equal to 1 to n AR cross Fr. Okay, so this we have discussed. Okay, so this whole system of forces is equivalent to a single force R and a couple of moment. Okay, so let us plot this once again. So we have rigid body like this, and we have a points A1, A2, A3, and we have An. Okay, and this is the, let us consider O as the origin of vectors, also known as base point. Okay, and the position vectors are, this is A1, this is A2, this is A3, and this is An. Okay, and the forces are F1, this is F2, this is F3, and this is Fn. Okay, so this whole system is equivalent to a single force R. Single force, let us write down here. So this is equivalent to a single force R plus moment. Okay, moment G. Okay, so this whole system of forces equivalent to a single force R plus moment, couple of moment G. Okay, R is a single force acting at O. Okay, so we have R is equal to summation R is equal to 1 to n Fr, and G is equal to summation R is equal to 1 to n AR cross Fr. Okay, so let us further simplify this. Okay, now let us consider the resolved part of, okay, let us consider the resolved part of Fr along x direction as xr, resolved part of Fr along y direction as yr, and we have resolved part of Fr along z direction as zr. Okay, so we have Fr as xr I cap plus yr j cap plus zr k cap. Okay, so R is equal to, resultant R is equal to summation R is equal to 1 to n Fr. So this is equal to, Fr is equal to this value. So this is summation R is equal to 1 to n xr I cap plus yr j cap plus zr k cap. Okay, so this we can further simplify as summation R is equal to 1 to n xr I cap plus summation R is equal to 1 to n yr, this is j cap, plus summation R is equal to 1 to n zr, this is k cap. So this is nothing but capital X, this is nothing but capital Y, and this is nothing but capital Z. Okay, so we have R is equal to capital X I cap plus capital Y j cap plus capital Z k cap. This is the value of R. Okay, now let us calculate the value of couple of moment. Couple of moment, how we can find this? Also, let us consider, so this we have considered a rigid body. Okay, let us consider a point AR, and we have the force what we have considered as FR. Okay, now let us consider these coordinates with respect to the base point is, with respect to the base point O is, coordinate is XR, YR and ZR. These are the coordinates. Okay, and the resolved part of resolved part of FR along X and Y direction, X, Y and Z direction, we have considered as capital XR, capital YR and capital ZR. These are the resolved parts of the forces FR along X, Y and Z direction. Okay, so now we have the value of G. So G is equal to, let us calculate the expression G. So G is equal to summation R is equal to 1 to N AR cross FR. Okay, so this we can write as summation R is equal to 1 to N. This is XR I cap. This position vector AR we can write as this in the terms of coordinates. So XR I cap plus YR J cap. These are a small XR. Okay, plus ZR K cap. Cross product with, let us erase this. With FR we can write as XR I cap, capital XR plus capital YR capital YR J cap plus capital ZR K cap. Okay, so let us take the cross product. So we have AR cross FR, summation R is equal to 1 to N is equal to summation R is equal to 1 to N. Let us take the cross product. This is I, J and K. This is XR, YR, ZR. This is capital XR, capital YR, capital ZR. So this is equal to summation R is equal to 1 to N. This is I. Let us take the cross product. This is YR, ZR, capital ZR minus ZR, capital YR plus this is plus J cap. Okay, J cap. This is ZR into capital XR, ZR into capital XR minus XR into ZR plus K cap. This is XR into capital YR minus YR into capital XR. Okay, let us further simplify this. Let us further say this is the value of G. So G is equal to summation R is equal to 1 to N. This is YR ZR minus ZR YR. Okay, I cap plus summation R is equal to 1 to N. This is ZR capital XR minus XR ZR. Okay, J cap plus summation R is equal to 1 to N. This is XR capital YR minus YR capital XR. Okay, K cap. So this is nothing but, this whole expression is L, this whole expression is M, and this whole expression is N. So G is equal to L I cap plus M J cap plus N K cap. Okay, so let us write down once again. So we have the R is equal to, resultant R is equal to X I cap plus Y J cap plus Z K cap, and G is equal to L I cap plus M J cap plus N cap. Okay, so these are the L, M and N are the sum of moments, moments of forces along. Let us take the coordinate axis like this. This is O, this is X, this is Y, this is Z. So this is OX along OX, that is X axis. Okay, along OX. So L is along OX. OY, this is Y axis. So m is the sum of moments along y axis, and n is, this is oz, that is z axis. Okay, n is the sum of moments along z axis, okay, respectively. Okay, so now let us prove this. So we have, let us take two cases. So in the first case we have conditions are necessary. Okay, and in the second case conditions are sufficient. Okay, so conditions are necessary and conditions are sufficient. Okay, so we have conditions are necessary, conditions are sufficient. Okay, so what we will do, so if the body is in equilibrium, if the body is in equilibrium, then there is neither translation neither translation nor rotation, nor there is rotational motion, neither translation nor rotational motion. Okay, so since there is no translation, this means r is equal to 0. Since there is no rotation, then g is equal to 0. Okay, so r is equal to 0 implies x I cap plus y j cap plus z k cap is equal to 0. This means x is equal to y is equal to z is equal to 0. Secondly, we have, since there is no rotation, then g is equal to 0. This implies l I cap plus m j cap plus n k cap is equal to 0. This implies L is equal to M is equal to N is equal to 0. Let us read down the statement. So we have the necessary and sufficient conditions of equilibrium of rigid body under the action of system of forces acting at any point of it are that sum of resolved parts of the forces along three mutually perpendicular axes. Okay, so these are the sum of resolved parts of the forces along three mutual perpendicular axis vanish. Okay, so this is equal to 0. Okay, vanish separately. Okay, secondly, we have sum of moments of the forces, sum of moment of forces along ox, oy and oz. Okay, so both are vanishing separately. Okay, so the first part we have proved. Now secondly, we have the conditions as sufficient. Okay, so let us consider, so let us take other way around. This means the x is equal to y is equal to z is equal to 0. Okay, so we have considered the sum of resolved part of forces along three mutually perpendicular axis as 0, and the sum of moments, that is L is equal to M is equal to N is equal to 0. So these are vanishing separately. Okay, so this implies that R is equal to 0, and this implies G is equal to 0. Okay, because R is equal to x I cap plus this one. Okay, so since x and y z, x y and z both all are 0, all three are 0, so this means this value of R is 0. L, M and N all are 0. This means G is equal to 0. Okay, so this implies that both the conditions imply that the body is in equilibrium. Okay, hence we can say that if the body is in equilibrium, then the sum of resolved part of the forces along three mutually perpendicular axes, that is OX, OY and OZ, and the sum of moments of the forces about these axes must vanish separately. Okay, so we will discuss further in next particular lecture. Thank you.